Okay, so I feel like we need more practice and on linearization problems, section 3.9. I wanted to do just two problems with you that I've snipped from the online textbook, and I think these examples are not too complicated that we can begin to wrap our heads around the concept of linearization, and I'll really try to actually explain it better than I think I did in class. So here we go. Find the linearization L of x at a point x equals a. So they give us the function, they give us some point, a equals -3, some x value, a equals -3. This is the answer, just ignore that temporarily. That's the answer. I had done that on my math lab and typed it in. I just want to show you how to get to that answer. So first we'll just perform the mechanics. So you know that to perform a linearization, that's going to be f of a plus f prime of a times x minus a. Okay, so first we just solely sort of like following a recipe, and then we talk about what it really means right at the end. Okay, so function evaluated at a, so all you're going to do is store -3 into your original function. So actually I'm going to lay out sort of the pieces of the puzzle here. So f of a is equal to 2 times -3 cubed plus 5 times -3 minus 4. Okay, go ahead and type that out in the calculator, crunch it out. I'll hit pause. And you can hit pause as well if you like. Okay, so hopefully for that first part, you got that the function, that would be actually evaluated at -3. So function evaluated at -3, you crunch that out and you arrived at -73. Okay, it's like a puzzle, so now you know that's what's going to go here. Now let's do the function prime, f prime, evaluated at -3. So I'm just going to scoot the paper on down here, and you can kind of lay the groundwork like this. Well, f prime evaluated at -3, and you might even want to go back up to the original and just kind of note to self of what f prime of x is. The derivative is 6x squared plus 5. So therefore we're taking 6 times -3 squared plus 5. I'll hit pause as we crunch that out. Okay, so you crunch that out and hopefully you got 59. Now you just keep laying that groundwork. As the recipe says, f of a plus f prime of a times x minus a. So then in the end, when we get our linearization, that's going to be -73 plus 59 parenthesis x minus c x minus a, but your a was -3. Now that is technically right. You obviously have to clean it up a little bit, right? So negative times a negative is a positive. 59, you know, you want to distribute that, send that through. So 59 times 3 is 177. So I can even scoot that down. Kind of running out of space there. But you basically have -73 plus 59x plus 177. And you keep cleaning that. And you will eventually arrive at the answer that I had typed in. See? The 104 plus 59x. So in terms of an exam, sure, you have to be able to perform the mechanics of that and getting that linearization and going from here to here. That's all mechanical. That's all algebra, plug and chug, really. But the big thing is the interpretation of it. So the thing that I wanted to get through in class, and I'm not sure that I did, was that the whole point of a linearization, and I really wish I would have said this in class, the whole point of a linearization is that this function here behaves like L of x so long as you stay arbitrarily close to -3. So I'll say that again. The original function behaves in quotes, like it's approximation, as long as you stay really close to -3. So okay, so this, now that we saw the sweat equity that went into that, so this function, this original function, behaves, or it's sort of like can be modeled by the equation of its tangent line as long as you stay really close to -3. For values close to x equals -3. Now what's really neat is let's run an experiment. It's like, oh yeah, pick something really close to a equals -3. Just let's see. Okay, let's go a little bit, you know, to the right of -3. So maybe -2.9. Let's see just how close the true versus the estimate is. So let's look at the function, original function evaluated at -2.9 versus, just think of it like that, versus your linear approximation evaluated at -2.9. Okay? So that's really all I was trying to get across, is that it behaves. So in other words, these values, you know, better be arbitrarily close. So let's just go ahead and take a look. Let's store -2.9 into the original function. So function evaluated at -2.9. All you're going to do is take -2.9, store it into the original function. Then I want you to take -2.9 and store it into the linear approximation. And that's a lot of number crunching there. I'm going to hit pause and let you do that. And you see if you match up with me. Okay, so hopefully you did your number crunching along with me. So the function, original function, evaluated at -2.9, after you plug -2.9 in there for x, you should get out -67.28. Then take your linear approximation, plug in -2.9, and guess what? You get something fairly close, -67.1. So the difference, you know, the true value minus the estimated value is small. -67.28 minus -67.1. You're looking at a difference of like 0.18. In absolute value, 0.18. So now you say to yourself, all right, so as long as I stay close to that point, the function behaves like its linear approximation. Well, how close is close enough? That's going to get discussed later in, you know, later in chapter 10. But it makes sense that if you go far away from -3, then this is no longer a good model. It would be a crude model. Okay. I do have another problem that involves finding a linearization of a trig function. In fact, and that's the last one. So now that you're comfortable with the algebra of that, I think we can just scoot on down to that one. Let me kind of twist that here if it'll let me. So I'll rewrite it. It says that the function is y equals tan x, and we're given x equals pi, so that's like x equals a. We're given some x value, arbitrary x value. It says to find the linearization, L of x, of the function tan x at x equals pi. Well, I have already typed in the answer here, but the question is, how did I get it? So again, now you know the command of the language. As soon as it says find the linearization, you just write down your formula, which is f of a plus f prime of a times x minus a, and you start plugging and chugging. So, you know, your function evaluated at pi, well, tan pi plus your function's derivative evaluated at pi, so derivative of tan is secant squared, so secant squared evaluated at pi times x minus pi. Now, like I said, if you arrive there on a test, I'm super happy. And it's right. You just got to keep cleaning it up. So let's scoot that on down. Now you're thinking back to your unit circle in trigonometry, and hopefully you're remembering pi is over here. So tangent of pi is going to be what? 0? Okay, so this will come to be 0. Secant really means 1 over cosine, so you're really looking at 1 over cosine of pi, whole thing squared, or 1 over cos squared pi. So with that, you could even rewrite it if it helped you. You could write 1 over cos of pi, whole thing squared. That's what secant really means. But you're quickly realizing that cosine of pi is -1, so -1 squared will come to be 1. So this whole thing right here will come to be 1, will end up being 1. So this is going to clean up. Let me scoot that down. So this is going to clean up then as 0 plus 1 times x minus pi. So it cleans up immensely just because of the trigonometry. And so then we end up at just L equals 1 times anything is itself, so just L equals x minus pi. And now here is the kicker. Let me go back to that. See, that was the answer. If I zoom in on here, I'll circle that in black. See? I had already typed that in. So the linearization is x minus pi. And again, all that means, if you have to make a sentence about it on the test, all that means is that tangent x behaves like this linear function as long as you stay in and around pi, close to pi. What does close mean? We don't discuss that to chapter 10. You definitely, it's logical that that's going to be a crude model if you walk out to say 10. You know, 10's way too far. You'd have to perform a different linearization. But here's an interesting experiment. Go near pi. Pi is 3.14, right? Walk out a little bit. 3.2. Go ahead, I'll hit it with you. Hit tangent on your calculator. Hit tangent of 3.2. So investigate how, I'm even going to write this here, how good of a model, is it a crude model? Is it? And just investigate at 3.2. Question, question, question. So again, just plug 3.2 in here and into your original and look at the difference. Okay, so tangent of 3.2, and make sure you're in radians. So tangent of 3.2 is about 0.058. So I'm just going to make a mention here. Tangent of 3.2 is about 0.058. Now, check this out. What's the linearization at 3.2? Well, that's just going to be 3.2 minus pi. Okay, well, 3.2 minus pi, look at that. Oh my goodness, it's almost exact. It's 0.0584073. That is amazing. You have to check that out on your calculator. They match up real close to like 4 decimals. So, you know, as long as you stay near pi, tangent behaves like x minus pi. That's the best way I can say that. Okay, good luck out there.